Good afternoon, and we were discussing nuclear power reactors in introduction because this is the course is principles of thermal energy conversion. So therefore, it's only introduction. We are not going in detail the reactor technology and so on. I have given these details in earlier classes with the difference between chemical and nuclear equation and the basic principles of nuclear energy conversion, and then what is the difference between fusion and fission reactions, and then these fissile and fertile materials. So the nuclear fission reaction, how it takes place and what are the components involved in that, and how the fuel is converted into various fragments, fission fragments and fission products. Then we also saw the energy from fission and fuel breakup in the previous class, and these are the overall energy released by a nuclear reaction or fission reaction. So radioactivity, thermal neutrons, we discussed what is the importance of moderator, how the net fast neutrons, how they are made into the same fast neutrons by a moderator and appropriate reactions. So this also we discussed what reactor components in the previous class, and fuel rods, uranium fuel, and here we discussed, I think, made graphite or heavy water are the moderators. Now today we will discuss various reactors. We will try to complete today maybe in another 1.5 hours time the entire course. Yesterday we could not attend because of there is a problem with the room, this availability of this room. So typically the nuclear reactor looks like this. Here it is a reactor where it is filled with fuel rods or bundles. Then the circulating fluid is sent through that. When during the nuclear reaction, whatever heat is generated by the nuclear reaction is carried away by this fluid here. So therefore circulating fluid needs to be such a way that it carries away the heat, and but in order to control the reaction, there is a control rods, and which is pulled and pushed down and up, so that the reaction is maintained, sustained. So here the coolant is an important fluid, and the coolant is mainly responsible for transferring heat from the fuel rods, and it should have some desirable characteristics, this fuel coolant that includes high heat capacity and low viscosity, because pumping power should be minimum, and low melting point, and then chemically inert. These are the three desirable characteristics of coolant. And cooler, it also cools the rods, fuel rods, and take away heat into boiling vat or boiling water. This is generally, the coolant is made of liquid metals or heavy water. These are liquid metals like sodium can be used, or water, heavy water is used here. The control rods, which is here, which they are transversed, or they pushed and pulled out depending upon the reaction conditions. The control rods are used to control the fission rate. Of course, they are thereby controlling the neutron flux. These they are also made of mainly neutron absorbing materials, and they should have high capture cross section, and they are composed of material like boron, silver, indium, and cadmium. Mainly they are made of cadmium or boron, and it absorbs extra neutrons to keep the fission reaction slow. That is why we use control rods, and of course lower or more control rods, that means slower reaction. Raising the control rods means faster. If you pull it down, push it down, then the reaction becomes slower, and if you pull it up, then reaction becomes faster. This is the basic concept. Then we will look at there is a overall how the but it is a very simplest form of reactor principle, but they are not, it is not so simple as this, but the basic principle behind the reactor is this, but we will discuss how what are the different types of reactors and how are they are operated in order to get the power generation or power production. So, there are two types of reactors, one is thermal fission reactor and fast breeder reactors. Thermal fission reactors are mainly different, again consist of various classifications which include light water designs, mainly light water means ordinary water, H2O. Light water is based on this, and which includes the PWR, that is a pressurized water reactor, boiling water reactor. Whether the normal water, the light water, when you send the water into the as a coolant, it can become vapor and directly that steam can be used to drive the Rankine cycle, that is called boiling water reactor. But sometimes the boiling water reactor may not be advised. So, in such case you go increase the pressure of water, where the boiling point of water increases. So, you can still operate in a liquid condition and then bring it to outside and transfer the heat to another water, that means another working fluid then to evaporate that. That is a pressurized water reactor, where the high pressure water is circulated into the reactor. Then heavy water, this is referred as a CANDU, Canadian deuterium uranium reactor. This is CANDU reactor is mainly based on Canadian design, and gas cooled designs, which includes this General Atomics HTGR, that is high temperature gas cooled reactor. I will explain what is that, and CO2 cooled designs, which are generally be British ones, and then German HTTR, that is thorium high temperature reactor, and then graphite moderated reactors. If you look at the other side, fast breeder reactor, these are liquid metal fast breeder reactors or LMFBR, then the other one is a gas cooled fast breeder reactors. We will discuss these in detail, how they what is the working principle of these and how they are working. So, if you look at the summary of commonly used fission power reactors include here, they are thermal reactor, fast breeder reactors. Here you can see all these are listed here, and the coolants are given here, water or light water and CO2, helium and D2O in case of these thermal reactors, but again moderators are these. Then you have fuel enrichment, that U2O, this low enrichment, low percentage of enrichment, whereas fast breeder reactor, so liquid metal sodium and helium are used, and moderator may not be required in this case. So, therefore, the fuels are plutonium oxide and uranium oxides, combination of these. The first we will discuss pressurized water reactor, which is a light water. In this case, actually I will go directly to this one. See here, the water is used as a coolant. So, therefore, since it is a pressurized, so there is no boiling takes place in the reactor. So, therefore, the coolant is pressurized to a higher than the saturation pressure corresponding to the maximum coolant temperature in the reactor. So, there are two loops are there, primary loop and secondary loop, where primary loop is the coolant loop, which is again light water, but it is a high pressure water. Working fluid is same as the Rankine cycle water liquid. So, water is evaporated and used for that. So, if you look at this, the first loop is, see, this is the reactor which you have seen, the fuel rods are undergoes reaction, and then the moderator control rods are adversed here, and this is a reactor vessel, and the high pressure water is circulated into this, and then it goes in a circular manner, and it picks up the heat here and then delivers here. So, this is a pressurizer, very high pressure water is used here. Then this liquid water which is in the liquid form at a high pressure gives back the heat to the another working fluid, that is water, and this is actually referred as a steam generator or boiler, and then it produces such superheated steam, and that steam is expanded in a turbine, and again this is the same as the Rankine cycle here, Rankine cycle. Okay. So, this is a same cycle as this, and then this part is same, only the difference is the primary loop which is under high pressure, that is a one. So, here PWR reactor vessels and internals, how they look like is the reactor contains about total 121 of fuel assemblies. Here this, in this case this is a fuel assembly, and with 33 contain control rod clusters, and the fuel elements include zircon CAD rods, clad rods, and then whose size is this 0.422 inch diameter or outer diameter, contains UO2 pellets, and each of this diameter and this one. These are some of the details of that. So, a typical plane view of cross section, if you look at, if you cut it here, if you cut like that here, this will look like this here. The reactor looks like this. You have a fuel assembly, control rods assembly, in core instrumentation location, and reactor vessel is outside here, thermal shield you have, core barrels, and of course surveillance specimen holder tubes. This is a cross section of that reactor. You can see the orientation of that as well. Then fuel assembly is another important here, because fuel assembly you can see here, the fuel assembly is this is the fuel assembly here. So, it looks like this. Fuel is loaded with in 3 approximately equal volume of concentric regions in the core of 40, 41, 40, 41 fuel assemblies, sub-assemblies. In this the first core is enrichment of 3.4, 3. These percentages in outer tube, immediate and inner regions respectively. So, the refueling takes place according to the inward loading schedule. So, therefore, each control rod cluster is composed of 16 control rods that are inserted directly into the 6 guide thimble welded into grid and top bottom nozzles of the fuel assembly here. And the control elements mainly fabricated by silver, indium, cadmium, these are the respective percentages alloy, and they are clad in stainless steel, and it looks like this here. You can see the bundle of so you can see these pellets, nuclear fuel pellets are placed here, and then there is a cladding over that, and the entire called fuel rod, and these fuel rods are put into guide tubes here. This is a guide tube here, and then inside, and there is this is a guide tube here, this is a instrument tube where data is taken here. All these put it into this fuel bundle, and they are in a regular interval. You have spacers to keep them intact here. This is a typical PWR fuel assembly, and how they are adverse, they put it into this entire assembly, put it into the reactor, which you have seen the cross section of the entire reactor cross section. This is one fuel assembly here. This is advanced into that, and you have a control rods adjacent to these ones. The next one, that is a working principle of that. The difference between boiling water reactor here is, if you look at that here, so you have 2 loops. So, therefore, the efficiency of this plays an important role. So, but you have additional advantages. This water needs to be pressurized. Instead, why don't we why should we have a primary loop at all? Then instead you can send this directly water into this and get the steam and run the turbine. So, that is a direct boiling water reactor, where the water is boiled within the this one. It is similar to conventional fossil fuel boiler plant, and the coolant is in direct contact with the heat produced nuclear fuel and boils in the same containment or compartment, in which the fuel is located. Because of water vapor coexist in this, so it produces saturated steam about 285 degrees and 70 bar, and this coolant serves as a triple function. It also acts as a coolant, moderator and working fluid, 3 of them in this. So therefore, it consists of a reactor, a turbo generator, condenser. So this is a Rankine cycle and feed pump here. So if you look at that, it is a simple one compared to that, but only thing is you get here low pressures and low temperature here, 70 bar and saturated temperature here, because you know that in once through boiler supercritical pressure boiler you have both, and in a general fossil fuel based power plants you have 3 components superheater, but this does not have a superheater, that is why you get only saturated water, that is saturated steam, saturated steam here. And the working principle is simple. This is again Rankine cycle. Instead of conventional boiler here, you have a nuclear reactor, that is all. That is a difference, and the rest is same, but everything will be in content, but of course it has its own advantages, limitations, because here performance point of view is better because there is no heat exchanger involved in this. Boiling water reactors, because it is already mentioned that water core exit quantities are low and between 10 to 14%. The quality is that, so that the recirculation ratios in the range of 6 to 10 are common. What is the meaning of this here is, suppose here if you do not get required steam here, what you do is bring it here and recirculate that. So, because if the exhaust steam quality is not very high, then what you do is bring it back and recirculate. So, therefore, you have to circulate 2-3 times, that is what he says. It says that 6 to 10 times it is a recirculation here. So, it is necessary to avoid large void fractions, that is, for void fractions means you know that the this is saturated steam which contains both vapor and liquid. So, therefore, the voids in the core need to be avoided, which will be which would materially lower than the moderate power in the coolant possible result, and low heat transfer coefficients and vapor blanketing and burnout possible, because there if there is a possibility of voids, what happens within the reactor here, if you look at, so what happens is here, if this you see here it is a liquid and it is a two phase mixture, and because of two phase mixture if there is a void formed here, and that is the possibility of uneven heat transfer coefficient. So, that results in burnout, that is the meaning of here, this burnout is possible. So, if you look at the assembly here, it is 12 feet active length, enriched U2O pellets, and fuel assembly is in this format, 7x7, 8x8 arrays, and enriched with Zirco alloy 4 channels, and then the control rods is mainly they are in cruciform in shape and occupies shapes of the 4 channels here. The control rods enter reactor vessel from the bottom, whereas in the previous case from the top. So, and it is mainly the actually neutrons are absorbed here and low part where the control rods are most effective, and this is saturated vapor directly into the turbine, which contains about 0.4% moisture. Generally we know that we go for 88% for turbine maximum. So, but actually what happens is at the end of the exit at the here the difference is, if you look at cycle, see what happens is at the end we have to have 88%, but here this is a saturated turbine here. So, it is still it is not complete 100% dry steam, you have 0.4% moisture, that means it is a 99.6% steam dryness fraction, and it is expanded like that, and then it goes like this. So, this is the one, not there is no superheating here in this case. Advantages is very simple and relatively low capital cost, because of the direct loop arrangement there is no heat exchanger just now discussed, and because of the large steam volumes above the water there is no pressurized is needed. But drawbacks are it is not this, because the reactor is not load following, because this is bypass control, because what meaning of this is because it needs to get the required level of this steam, it needs to be recirculated. So, therefore, it needs to be corrected such a way that this bypass control is required, and loss of neutrons due to water absorption, hence its increased power, and recirculation control is a problem, because in the just now I mentioned that you need to recirculate 6 to 10 times. So, therefore, there is a drawback of that. The next one is the gas cooled reactor. This gas cooled reactor is instead of liquid thing, you can go for heavy water moderated and gas cooled reactors. They are important, and it has a attractiveness of gas cooling. In fact, it is gases are safer. So, that is why it is used, and they are relatively easy to handle. That means, you are sending gas into the reactor, unlike water, have low microscopic neutron cross sections, and are plentiful and cheap, because only except helium other gases are cheaper, and may be operated high temperature without high pressurization. But disadvantages include low heat transfer, because gas as compared to liquid, gas is a low heat transfer coefficient, and heat transport characteristics are lower for this, and of course, liquid requires large contact surface because of low specific heat capacities. So, therefore, the flow passage within the reactor and heat exchanger are important here. But it is a high pumping requirement, because you are sending the compressing the gas. So, therefore, 8 to 20% of the parasitic power is required for pumping it. So, up to 20% for pumping the gas into that. So, gas cooled reactors are inherently large, they are particularly suited for large capacity power plants, and also good fuel burn up and conversion ratios. And typical advanced gas cooled reactors are this, mainly gas here is the CO2. CO2 is one of the fluid here. So, look at the system here. This gas is the reactor with control rods. You have it is made of steel lined concrete pressure vessel, the entire thing, but it is a biological shield. Then inside the gas is circulated here, and the gas goes here. It is a periphery of that. You see, if you look at the cross section, you have a cross section like that here, and what happens is you have this assembly in this, but you have in the jacket you have heat exchanger network like that. That means, the gas heats up from the center, you mean to say here is the gas comes like that and goes here, and then it heats up the water, then gas is cooled, then the fluid liquid goes into this through the heat exchanger, but this is a circumferential, and all these pipes are connected, and then it produces steam here. This is a steam which is going out from the boiler, and the steam is the rest of the part is same. This is the Rankine cycle, and of course, this is a cooling tower, all this. Here the CO2 picks up the heat from the nuclear reaction, and then the hot CO2 is cooled. That means, the control the fuel rods are cooled by the CO2, and whatever heat picked up by the CO2 is given in the boiler in order to convert the liquid to steam, and the steam is further expanded in the turbine. This is the same as that, and a typical system looks like this here. This is a heat exchanger, this part is heat exchanger, but why the other side is shown, because it is a circumferential, it is not only one, it is since you have seen as a cross section. So, this part and this part is same, since you are looking at the cross section, so you are seeing the other side also. This is all around here, all around, and circumferential one. So, here you can see the gas, there are two, you see these are the pumps to circulate gas. Gas is pushed, CO2 is pushed into the reactor here, and then goes to the heat exchanger, and these are control rods here. The gas cooled reactors are inherently very large, and they are particularly suited for large capacity, this which we have already discussed, and the size of this can be reduced by a certain extent by fuel enrichment. Next one is pressurized heavy water reactor. Because in the previous one we used pressurized light water reactors, where the normal water H2O is used, but if you use D2O, then how it works out in under pressurized condition. So, heavy water reactors are operated at high pressures than the light water reactors, the previous one. The pressure ratio is comparatively higher in this case, and D2O is different nuclear characteristics, and as a moderator also it requires neutron to travel about twice as fast as far as ordinary water in order to lose the same energy fraction. That means, here neutron travels longer distance than the normal water reactors. So, D2O absorbs practically no neutrons. So, therefore, D2O is used as a coolant come moderator with the neutral and natural uranium fuels, that is U-238. So, D2O is also results in a good fuel burn up and conversion ratios, and economic advantage is low cost natural fuel because of the absence of very costly enrichment process, because it is not U-235, it is a U-238, because the 2 to 3% enrichment is not required. So, therefore, natural uranium can be used this one, but the absence of critical hazards during the fuel fabrication. The overriding of factors in this includes high capital cost, large expensive heavy water inventory, because heavy water needs to be produced, and couple of because production of heavy water from light water is also very expensive component. So, it coupled with the high fixed charge rates. This is it requires long neutron paths for moderation. So, D2O moderator reactor requires large moderator to fuel volume ratios. So, therefore, it requires larger, thicker and pressure vessels are important. These larger, thicker and costlier pressure vessels are required in this case, because the pressures also higher as compared to light water reactors. These are some of these, and if you look at how pressurized heavy water reactor looks like, the difference here, this pressurizer, here you see that the steam generator here, and you have heavy water coolant. This reactor is same here, but if you look at the reactor here, this is fuel here, these parts are fuel here, this fuel are here, uranium, and actually you look at that, these are placed in this way, loading fueling machine is in this, like this is placed here, and reactor is this, and heavy water moderator is filled in this, and you can see that the working fluid, heavy water is circulated to this, and then it releases heat into the working fluid, that is water. This is H2O, this is a normal water, light water, this is a heavy water. So, heavy water coolant is it transports heat and transfers heat to the light water, and its steam. This is same as the Rankine cycle, all others are, this part is same, only the difference is here the configuration of reactor here. So, this part is called calandria, this part is called calandria, which because it is horizontal loading here as compared to the other side, sorry. So, this part is called calandria. Yeah. So, the It some allows the use of low pressure, less costly vessel, but it adds expensive to construction to leak type Calandria vessel, and is free from differential expansion. What the meaning of differential expansion is, when you absorb heat and release heat, see, because the high temperature D2O goes into this, and then when it releases heat, then it becomes cooler and then it goes back. So, therefore, there is a thermal expansion possible here. So, therefore, it should be airtight and it should be leak tight, this Calandria. So, problem associated with this is loss by leakage through expensive D2O. There is a possibility of this D2O leakage, and which is expensive, and high activity associated with the decay in tritium formed in the reactor. That is another problem. And if you look at the next one is this CANDU. If you say this is similar to the pressurized water CANDU, it is called Canadium deuterium uranium reactor. It is called CANDU, and natural uranium is used as a fuel and heavy water as a moderator and coolant, both moderator and coolant. This you have seen the same thing I am showing here in a 3-dimensional. This pressurized heavy water reactor is called CANDU. So, this CANDU, because it is a Canadian design. So, you look at it is the same thing, this part is horizontal, you have seen here in horizontal loading. So, therefore, the heavy water goes in a horizontal way and then comes out, and this part is called Calandria. And you have a pressurized here the moderator flows into this. This is a moderator pump here, and the moderator flows into this here like that. Is also D2O. Moderator is also D2O, and this part is a Rankine cycle here. This is a Rankine, same as the boiler, evaporator, and you have a condenser here, and this is a turbine generator here. This is called CANDU, and the entire system, both steam generator as well as the Calandria are in the this concrete containment here. See, this is a control one here. Containment is building is this. It looks like this picture. So, this horizontal Calandria reactor vessel, and fuel elements are containing natural uranium dioxide. So, therefore, and it is housed in a pressurized tubes, which also carries pressurized heavy water coolant. Then it consists of cool D2O moderator also in the shell, because you have seen this moderator here. The moderator loop is this, is also same as the coolant. The Calandria contains this some specification 390 horizontal pressure tubes, and it also Calandria and coolant tubes are separated by sealed aluminum annulus containing CO2, and these are inert gas, or there is less reaction between them, CO2 and in annulus, sealed annulus contains this. So, the Calandria is dump tank with heavy aggregate concrete. What is the meaning of this? Is this entire system which is located in the containment, that is shielded with that, and the dump tank contains helium atmosphere. And CANDU reactor fuel looks like this. Fuel bundle consists of fuel pellets, and this is you can see it is a kind of a circumferential loading here. So, this is a pressure, it is pressure tube, and it is placed into these reactors here in this. And you can see that it is radial. If you look at the top view, they are placed tubes like that circumferentially, this one. So, the fuel elements are hermetically sealed Zirco alloy with 2 rods that are containing compacted sintered, this is compacted sintered fuel enriched fuel pellet, and about 28 such elements are attached mechanically into the ends to form a cylindrical fuel assembly. This type of 28 pellets are placed in this one. Then this so far whatever we discussed are the thermal reactors. Then we will look at the fast breeder reactors. The fast breeder reactors, here the neutron flux spectra for fast and thermal neutrons I will show you here. What is the difference between fast and thermal reactor as far as the neutron is concerned. You can see this neutron energy versus neutron flux here is shown. You have a fast breeder looks like this here, and the thermal curve is this. When neutron bombards with the U-238 then it becomes U-239, and with half time of 23 half-life time of 23.5 minutes, and it beta and electrons are released from that, and then subsequently transformed into Neptune U-239-93, and again it releases, then it becomes plutonium here with so much lifetime 2.4 into 10 to the power of. This is a complete neutron spectra for this one. So, here generally no attempt is made to thermalize or slow down the neutrons in the fast breeder reactors. See, the meaning of that is when this neutron is released after reaction, the two or more than two neutrons are released, their speeds are very high. So, therefore, in a thermal reactors it is reduced, moderated, but whereas in fast breeder reactors it is allowed to go with the same this one. So, therefore, there is no slowdown of neutrons in the fast breeder reactor. Generally here the liquid metal cooled reactors, because the sodium or other liquid metals are used. So, therefore, an insignificant number of neutrons exist in the thermal range. So, therefore, for thermal reactors, which means the water moderated, the spectrum of neutron is in the fast region, that is greater than 0.1 million electron volts, has similar to that and fusion process it is emitted. And if you look at here, sodium is circulated with 10 bar and this through the reactor, and which comes with a 545 degree Celsius, and you have here the fuel rods with 15% enrichment, either it is UO2 or PuO2, that is plutonium oxide fuel, and it is of course depleted over a period of time, the outer side ones here. So, the core of fast breeder reactor consists of two parts, which includes fuel rods, which contains a mixture of uranium dioxide and plutonium dioxide. They are inner parts here in this case. This fission reaction dominates here, and while the outer one is predominant process is for conversion of U-238 to Pu-239 from here to here. The outer ones are from here to here. Okay. So, this part generally contains depleted uranium, that means as U-238 becomes 235 and then even lower lower than the natural 0.7. The meaning of this is here it contains depleted uranium, means the converted uranium, which contains less than 0.7% U-235, because it is even natural uranium, that is U-238 has certain fraction of U-235. In such cases this is a more fissile plutonium nuclei is produced in the unit time than the number of fissile nuclei which undergoes fission. So, therefore, that is why it is called a fast breeder reactor or fast breeder. It breeds faster, so and converts into plutonium. On the other hand, neutrons are not thermalized. So, therefore, since they are faster and are needed for above described process here, and fission, this is called fast breeder reactors. Next one is so far what we discussed is a fission based reactors. Now, look at fusion power reactors. I think lot of work is being done. ITER is the you look at in website. ITER is a program which is based on fusion based reactors that is still yet to be commercialized, and India is also part of that. So, this fusion power reactors means is opposite to that. This deuterium is stable heavy isotope of hydrogen, is mainly fuel for fusion reaction, and here the typical fusion reactions are shown here. You can see that how hydrogen is converted into helium, what is the temperature ranges, and what is the energy release here, and you can see these, and there are 4 reactions at different temperatures occur, and 4 different energy levels happens here. Deuterium tritium reactions occurs less than temperature as compared to the other reactions, which is involves actually more energy than these 2 reactions. Tritium is produced by lithium breeding blanket that surrounded by plasma core, and plasma is inside the evacuated tube. This is the operation, but you can look into that, and there is a vacuum wall surrounded by that. This energy neutrons pass through and it is maintained about 750 degrees Celsius. So, the lithium blanket and magnetic shields are placed around that. Advantage of this is abundant supply of deuterium, then is no radioactive waste is produced from fast breeder reactor because cycle is closed here, and then high energy conversion efficiency, easy to handle, and then low heat rejection surrounded by kilowatt generation, because that is a fusion basis. And typical fast breeder liquid metal cooling reactor here is this. It is same as which I have shown here. Liquid metals are used in this case. The coolant is a liquid metal, usually sodium, which we have shown. This I have already discussed, and it is a liquid. This is the liquid coolant. It goes into this one and comes back here in the reactor here. This is a sodium circulation here, and this is the same as the Rankine cycle from here to here. So, the sodium is sent to this fast breeder reactors and picks up the heat, and then this one it attains high temperatures and better efficiency. Faster neutrons are participating in fusion reaction. So, therefore, there is no moderator required, because no need to reduce the speed of that. So, therefore, surplus neutrons are used to convert the non-fissile materials into fissile fuel called breeding. So, just I have already explained. Typical I think there is a I am going back and forth. This fusion, see this is the same as that, but now if you continue from here, this is the conceptual deuterium tritium fusion power plant. Here you can see there are 2 turbines involved here. This is the vacuum chamber, vacuum plasma, and other chambers, and lithium tritium is used here. Then this is the working fluid which picks up the heat and then gives back into the potassium boiler, and where the potassium is converted into vapor and it is expanded in a potassium turbine, and then it is rejected here. It is like a binary, you have a binary power cycle. This is a topping cycle here and this is bottoming cycle. So, here steam is used as a bottoming cycle H2O, and then there is a same here, and you have here lithium blanket and liquid potassium comes here, it goes back here liquid and becomes vapor, and then this is a cycle. So, this the deuterium is produced from seawater. Then if you look at the advanced 4th generation designs, here is they are in modular size and sizes ranging from 150 to 1500 megawatt electric, and they are lead cooled RX optionally variable. It is a 50 to 150 megawatts battery is also connected with that, and the life is 15 to 20 years without refueling. Once that is fueled, it has a long life, because the specific energy is very less in these cases. Technologies used, operating temperatures, and deployment time is I think by 2030, we do not know, still it is not. This one 4th generation reactors are coming, but in between, because of the nuclear accidents, the nuclear activity has come down because of that Japan's accident during tsunami. So, I think most of these countries, they have stopped nuclear activity, but we do not know how, because they are trying to phase out. US is the highest, more than 100 nuclear reactors, they have not increasing, but Germany is they are planning to phase out soon, but I do not know what is the status here. This is a typical characteristics of that. Here it is helium cooled is used, and this is a lead bismuth, and of course, one uses sodium and uses fluoride salts coolant as a coolant, and there are different technologies which are used for as a fast breeder reactors. These are statistics. Countries involved are these here, and safety features, because here molten metal designs at lower pressure and higher temperatures are important, and it is employed in natural convection for coolant circulation. These are some details with which used as a fuel reprocessing on site, but India is also working on fast breeder reactors with a higher level. Once that is done, because we have abundant thorium reserves, thorium can be used for this purpose. So, with this this is other details. With this I end the topic here. So, I thought I will take more, but it is a. So, this is this topic is mainly on nuclear reactors. I have given you the brief introduction to the nuclear reactors, because as I mentioned, this course we are not going in detail how these, and there is a separate nuclear engineering courses, but you understood that there are thermal reactors, fast breeder reactors, and then you have wide variety of reactors which are used for producing energy, and there are some advanced reactors also. So, with this I end the course.